Good morning. Take my mask off so you can hear me better. I'm Dr. Bill Stewart, and I'm with you again to do some mathematics. In a previous class, we took a circle and we put inside that circle various polygons, starting with a triangle, equilateral triangle, working through a square, all the way up to an octagon. And then we did some mathematics to figure out the percentage of area that was covered by the polygon inside the circle. And we came to the realization back then that in a plane, 2 dimensions, as you increase the number of sides of the polygon, you had more and more of the area of the circle covered. And it gave us the thought that really a circle could be defined as a polygon with an infinite number of sides, because it would then cover itself. Okay? Now today we are going to move into 3 dimensions, and a lot of times when you go to 3 dimensions, your heart rate goes up and people start to get a little nervous. Try to illustrate to you, no reason for that. Just look at the figures, identify the various sides that are involved in the figure, and then do your calculations. So the first one we're going to do is a sphere inside a cube. So let me just draw a cube up here. I'll put some dotted lines. And of course a cube has the same dimension for each of the 3 sides. Okay, so that's our cube. I'll just write that here. And then we're going to put inside that cube, we're going to put a sphere. So I'll draw a circle, represent the sphere, and I'll put a little shading to indicate that there are 3 dimensions involved. Okay? So think about a box with equal sides, and we're going to take a spherical balloon, you might have at a party, and we're going to blow it up, and we're going to blow it up so that it just touches all the sides. Okay, so we're going to put the biggest sphere we can inside that cube. All right, so let's see how we might go about that. The volume for a sphere, so volume sphere, is equal to 4/3 pi r cubed. Okay? So whatever this radius might be, we cube it, multiply by pi, multiply by 4/3, and that'll give us the cubic units that the sphere would have. Now, for a cube, the volume of a cube is side times side times side. So that would be side cubed. So the question now is, we have dimensions of the side for the cube, and we have dimensions of radius for the sphere. So somehow we have to get those two to match up. Okay? So if we look at the circle, the sphere, inside this cube, I'm going to draw a projection of it just on the side, outside here. And what you'll see is that in the center, so let me draw a little line down here like this, and a little line down here like this. That's in the center. And then if we went across from there to there, again dotted because it's inside there, the sphere and the center of that line across there are going to coincide. Okay? So what we can say then is that if the side of the cube is S, then it is exactly the same as the diameter of the circle, or of the circle, which is the projection of the sphere. Okay? So what we're going to do then is say that the radius of the circle is going to be half of the side. So radius is equal to side divided by 2. All right? So again, repeating that, the sphere is centered with the center of the cube, so the center of the sphere is going to be the same as the center of the cube. And if we project that, then all the way across is the diameter. Half of that is the radius, and half of that would be s over 2. Okay? So over here then, I can plug this in, and this is going to be 4/3 pi. And now we'll take r and plug this into it. So I'll put a parenthesis there. So we'll say r is s over 2, and we're going to cube that. So now we can say that 4/3 pi, and now we'll just cube everything inside the parenthesis. So we'll cube the top, and we'll get s cubed, and we'll cube the bottom. 2 times 2 times 2 is 8. And so we get that expression, and I'll simplify that one more time. I'll cancel this out and make that a 2. And now I have 3 and 2 on the bottom, pi s cubed on the top. So we have pi s cubed on the top, and the bottom will have 3 times 2, which is 6. Okay? So now I have an expression for the volume of the sphere is equal to pi s cubed over 6, where s is the side of the cube. All right. Now, I can form a ratio of those two volumes, okay? And I'd like to know what percentage of the cube is taken up by the interior sphere, okay? So I'll do Vs on the top and Vc on the bottom, the cube, okay? So on the top, I will have pi s cubed over 6. That's on the top. On the bottom, I'll have s cubed. Okay? Now we can rewrite that and make this a fraction with that. So I'm going to have pi s cubed on the top of the big fraction. The 6 comes down here, so I'll have 6 s cubed here. And nicely, the s cubes cancel. There we go. And what I have then is the ratio of pi divided by 6. Okay? And if we do that on the calculator to find that decimal, we'll take pi, let's see here, divided by 6. And that decimal is 0.5236, rounded off. Okay? So about 52.33%, bit over half, of the volume of the cube is taken up by the volume of the sphere. Now, let's say you were in the shipping company, and you were shipping basketballs, okay? And typically basketballs tend to be in cubic boxes. Sometimes part of them shows out through a hole in the box. But now if you were shipping those, and you were a big basketball manufacturer, you would be shipping almost 47% air, okay? So in that box you'd have the basketball, and that's the space that it takes up, but then the cube that becomes the box, as they would stack up in a truck or an airplane or whatever, you would be shipping a lot of air. So you might say that if you're running Dick's Sporting Goods and you're selling hundreds and thousands of these basketballs during the fall and winter, there would be an incentive for you to have the basketballs deflated and shipped flat. So you could ship 10 or 20 of them in one little box and then blow them up once you get there, especially if those balls are being sent from China. Okay, so we can see then in the athletic marketplace, there are incentives, economic incentives having to do with shipping costs that would cause someone to actually bring in the product deflated and flat and then spend the money to have them inflated and displayed in the store. Okay? So I'm going to stop here for a second and erase the board, and now we're going to come back and reverse the process. We're going to take a cube and put it inside a sphere. Okay, welcome back. We're now going to do the cube inside a sphere. So here we have a big balloon. We're going to take a cubic box. We're going to put it inside that balloon. We're going to stretch that box until it touches the sides of the sphere. And now we're going to ask ourselves the same question. How can we relate the two volumes? And we'll try to find a percentage of the volume of the sphere that's taken up by the volume of the cube. Okay? So, let's start here. We'll just sort of label the circle has a radius right there. Okay? And of course, this is in 3 dimensions. We're just looking at the projection of that coming forward. And over here we have the sides of the cube. And let's label that. So again, we'll use S for the dimension of the side. So S there, and S there, and S there. And all those are equal, obviously. All right, so the first thing we need to appreciate is that when I put this cube inside the sphere, I'm going to center it up. Now, why do I center it up? Because that allows me to absorb the most volume of that sphere. So the center of this cube is going to coincide exactly with the center of the sphere. Okay, just want to clear that up because it's important when we do that, when we try to relate the radius to the side S. Okay, so now how are we going to what are we trying to find here? What we're trying to find is if we took this cube and we drew a diagonal, and I'll do that in a little different color. If I drew a diagonal from this corner to that corner, and I'll dot it because, there we go. And of course, right there in the center is the center of the sphere, or the center of the cube. If I knew what that was, if I knew what that diagonal was, then 1/2 of it would correspond to this radius. How do I know that? Because this vertex is going to be touching the edge of the sphere. Touch, 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 touch. 8 points is going to touch. That point will touch. This point will touch. It goes through the center. Therefore, by definition, it is a diameter. And then, if I know that diameter, I can divide it by 2, and then I'll have the radius. All right? So now we're going to do a little manipulation of this cube to try to find out how long that diagonal will be, and then we'll create a radius out of that. All right, so let's see how we would do that. The first step is to say, well, what are we really trying to look at in terms of a shape? So I would contend that we're going to try to get this triangle that's laid in this way, going from this down to that corner and going right through the center with this. Now we know this is a right angle, so that's going to be a right triangle, so that's nice, all right? But how do we find this dotted line across here that is the diagonal of the square S on each side? Well, we know how to do that too. If we look at that triangle, we have a side, and then we have the diagonal, and that's this dotted line here, okay? So I'll just call that, I'll just give it H for hypotenuse. This is going to be a right angle, which is this right angle here, inside there. So it's a right triangle here, 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 okay? We know that the sides of the triangle are S and S. We have a right triangle, so we can use our friend Pythagoras, and he would tell us that h squared, the hypotenuse squared, the length of the hypotenuse squared, is going to be this side squared plus that side squared, which is 2s squared. Okay? So this dimension right along here, put a little arrow out here, is going to be the square root of that, which is square root of 2s. Okay? Now, if I know that, now I have another triangle which has a height of s, a base of square root of 2s, and now I want to find the diagonal of the cube, which is again another Pythagorean calculation. So let's go ahead and draw that in red. Separate the two. So down like this, over like this, and then down like that. Okay. So we know this is S. That's this side right up here. We know this is a right angle. We are trying to find this, which I'll call D for diameter. And we know this side is the square root of 2s. Okay? Now, let's use the Pythagorean theorem again. D squared is equal to the sum of the squares of the two sides. Well, this would be S squared. And this would be this squared, which is nothing more than this. If you square square root of 2, you get 2. You square s, you get s squared. Well, that's handy. D squared is equal to 3 s squared. Okay? So what would D be? D would be the square root of that. So it would be the square root of 3, okay, s. Okay? So the square root of 3s. Now, we said we wanted the radius, okay, because we want to relate that to the sphere. So we'll just divide that by 2. So radius is equal to diameter divided by 2, which is the square root of 3 times s divided by 2. Okay? All right. Now, I think we're ready to do our calculation. We want to know what percentage of the volume of the sphere is contained in the volume of the cube. So we're going to take the volume of the cube on the top. We're going to divide that by the volume of the sphere. Well, the volume of the cube, we said, is s times s times s. So that's going to be s cubed. And the volume of the sphere is 4/3 pi r cubed. So I'll put this in here. Square root of 3 times s divided by 2, all that cubed. Okay? So, volume of the cube, s cubed. Volume of the sphere, 4/3 pi r cubed. R, square root of 3 times s over 2. Put inside the parenthesis and cube the whole thing. All right, so let's go ahead and do the cubing process. So we have s cubed here on the top, that's from the cube. I'll continue to do the whole fraction on the bottom until we have everything done. So there's our 4/3. We have pi with 4. Now, I'm going to cube everything inside here. When I cube the square root of 3, let's think what cubing means. You square it, which means you multiply square root of 3 times square root of 3, and then whatever that is, you multiply by square root of 3 again. So the square root of 3 times square root of 3 is 3, and one more cubing of this, one more multiplication of the square root of 3 would give us 3 square root of 3. So I'm going to keep the parentheses here for a second. So we have 3 square root of 3, that's the cubing of that. We have s cubed, that's the cubing of that, and 2 cubed is 8. All right? So I have s cubed on the top and all this stuff on the bottom. Let's deal with all this stuff on the bottom. Okay? So here we go. Here's my s cubed again. Now, let's do all the numbers. Okay, now I have no powers out here anymore, and I can really eliminate the parentheses. So on the top, I'm going to have 4 pi 3 square root of 3 s cubed. Okay, so I'm going to have 4 pi 3 square root of 3, and then I have the s cubed. What I have on the bottom, I have 3, 8, 3 times 8. Okay? Let me draw a little line to separate these two so we don't get the numbers confused. All right, so I can do a little canceling here. So I can get rid of the 3 here. I can get rid of the 4 and put a 2 here. Okay? So let's rewrite that again. Oh, I can also cancel out the cube roots of or s cubed. They're gone. Okay? So what do I have left? I have pi. Okay? I have a square root of 3, and I have a 2 left over because 4 canceled out and became a 2. Okay? So, now I can put that in my calculator, okay? And let's see what we get. We get pi times square root of 3, which is 1.732, and then divide that by 2, and I get, try that again, second pi, oh, that's on the bottom, sorry about that, I have 1 on the top. I canceled out the cube roots of 3. Now I have all this on the bottom. That's on the bottom. I got to flip it all over. Okay? So let's go ahead and do that. Flip it over. I get 2 on the top. I get square root of 3 times pi. Okay? Let's figure that out. So square root of 3 times pi is 1.732 times pi. So down here I have 5.44, and on the top I have 2. So let's take that, take 2 divided by that, 5.44, 0.3676. So, an interesting little connection there. When I put the cube inside the sphere, the cube only takes up 36.8% of the volume of the sphere. Whereas when I had them reversed, it was like 52%. Okay? So if you were going to package things in spherical packaging, and you were going to put toys that were cubic shaped in there, you would see that you'd be shipping an awful lot of air in that particular package. Okay? Now the final thing we're going to do in today's session is we're going to look at a shape called an ellipsoid. And since pro football kicks off tomorrow, I thought we would use a football to illustrate that. Let me prepare the board and I'll be right back to you. Okay, welcome back. The third problem we're going to do today has to do with football season. So tomorrow the NFL kicks off its season. It'll be a little different season than what we're used to. Very few fans in the stadiums and so forth. But the problem we're going to solve is taking a football, here's one, and we're going to put it in a box that's designed to sort of fit the football. So it's not going to be a cube, it's going to be a rectangular prism. And we're going to do the same calculation that we did for the sphere in a box, a sphere in a cube, and cube in a sphere. But we're going to do it for this shape. Now, this shape is very close to an ellipsoid. Okay? Now you've probably heard of ellipse as an orbit. Johannes Kepler figured out back in the 1600s that the planets revolved around the sun, and they didn't do it in circles. They did it in elongated circles, which were ellipses. And in some of your math classes, you've heard of the conic sections, where you can take a cone, you cut it different ways, and it creates shapes. The most popular one of those is a circle. There's a parabola, there are hyperbola, and there's also the ellipse. Okay? Now an ellipse is a planar figure, so it's two-dimensional. This obviously is 3 dimensions, and so we're going to deal with 3 dimensions with this particular shape. Okay? So we'll put this right here in front. Get it if we need it. Okay? So let's see how we can handle that. So if we draw an ellipsoid, shape similar to that, the ellipsoid has 2 axes. Actually, it has 3 axes. The ellipse has 2 axes, a planar figure. Has a major axis that goes on the long dimension, has a minor axis that goes this way, up and down, and that would be the case if we were in an XY plane, X, Y, but we're in XYZ plane, Z, okay? And so we're going to have an axis coming out of the board, which is very similar, in fact, exactly like the axis going this way. So the axis going in and out of the board is exactly the same as the minor axis here. So our ellipsoid is going to have 1 major axis and 2 minor axes. Okay? Now here's the interesting thing. To find the volume of an ellipsoid, it's very similar to the volume of a circle. And to derive that takes a lot of mathematics. We're not going to get into all that and some proofs and so forth. But here's what comes out of it. That the volume of an ellipsoid is equal to 4/3. You've seen that before. Pi. And then we take the radii that are in these dimensions and just multiply them together. So we'll call this R1, major one. We'll call this R2. And then the one coming out of the board will be R3, out of board. And here's how we handle them. We multiply R1 times R2 times R3. Now that's interesting because for a sphere, it's 4/3 pi R cubed. But since these R's can be different because of the different axes, we multiply them separately to create the volume. Okay? All right, so let's do that. So we'll call this R1, this distance here. We'll call this R2. As we said, R3 comes out of the board. Now we're going to put this in a box. Okay? So the box has dimensions. Okay? And basically, the length of the box is going to correspond to the major axis. The width of the box is going to correspond to the minor axis. And the depth of the box is going to correspond to that same minor axis. Okay? So, that box, the volume of the box, is going to be what? Well, if this is R1, then that dimension is going to be 2R1. And if this is R2, this dimension across the box, width of the box, is going to be 2R2. And then coming out of the board, same as that, just flip 90 degrees, is going to be 2R3. Okay? Now we will make R1, R2 and R3 equal in a second. Okay? So let's see what that is. We multiply the 2's. 2 times 2 times 2 is 8. And then we have R1, okay, and R2 and R3, okay? So that's going to be the volume of the box that the ellipsoid or football goes into, all right? Now I should label this, that's R3, not R cubed, I'm sorry. Okay, so we have this as the box volume, we have this as the volume in the ellipsoid. So let's form the ratio. The box is the bigger, the ball goes in the box, so we're going to take the volume of the ellipsoid. It's going to be equal to 4/3 pi, and we'll just write it out, R1 times R2 times R3. Realizing R2 and R3 are going to be the same. We divide that then by 8, R1 times R2 times R3. Okay? Well, guess what? The R's go away. Okay? And all we have left are fractions and pi. So let's now write this as one big fraction then. We have 4 pi on the top. This 3 comes down here, and that's 3 times 8. Okay? Now, this 4 can cancel this out, make that a 2. So what we have is pi on the top, and 3 times 2 is 6 on the bottom. Now, where have you seen that before? You saw it a few minutes ago. The ratio of the sphere inside the box, okay? If we calculate that again for a number, okay, we take the pi and divide it by 6, and we get that same decimal, 5236, that we had with the sphere inside the cube. So that's an interesting situation where you have a shape like this, very different from a sphere, okay? And when you do the calculation for the shape that it goes into, you come up with exactly the same percentage taken up by the shape inside. Sphere in the one case, ellipsoid in the second case. Which would tell us then that the ellipsoid, if you would collapse it so the major axis is the same as the minor axis, so those became symmetrical, then the ellipsoid becomes the sphere. Okay? And the rectangular box becomes the cube. And therefore the ratios are exactly the same in the limiting case, but they're also the same for any shape of the ellipse and the box, ellipsoid in the box, that you might run into again in a business or manufacturing situation. Now these are popular type problems on standardized tests. One, because they force you to deal with some geometry, they require some manipulation along the way of dimensions using variables, and then it forces you to form a ratio which can then become a percentage. Okay? So it's a very rich mathematical type of problem. So I hope you enjoyed that. I hope it took away some of the trepidation of dealing in 3 dimensions, and I wish you well in the rest of your day.